All right, good morning, everyone who is actually here. A lot of people today. Anyways, so I don't know if you noticed this morning, but the Wi-Fi was not working, so it's been kind of a terrible day so far. Tragic that it didn't work, but anyways, so let's continue the problem that we started on Friday. So just kind of remind you, so what I have here is a wire, which is that top one carrying the current, say, to the left, with 100 amps worth of current running through it. Down below that, then I have a U-shape, or in this case, rectangular shape, doesn't really matter, conducting rails, which then has a mass which is sliding on top of it. So this is a rod, which is some conducting rod, which in this case, I'm moving to the left at 5 meters per second, and it has a resistance of 0.4 ohms. And the conducting rails are 10 millimeters below it, so at the closest side, and that these things are 10 centimeters long. And then since this thing is moving to the left, we define this distance from the end as simply x, which is the distance it is from that end point. And we've been tasked to solve a whole bunch of different things. The first part was to figure out what is the induced EMF inside of this rod. So this is what we came up with last time. We just didn't plug it in numbers. But again, here, the trick was, because the magnetic field is not constant, the induced EMF is not simply the magnetic field times the length times the velocity, because in that case, that would be presuming that the magnetic field is constant, but here it's not. It's actually position dependent. So again, the further I get away from it, the smaller the magnetic field becomes. So the magnetic field up here is much bigger than the magnetic field down here, so we actually had to do that integral, which gives us this guy. So the EMF then, which is the time rate of change of the magnetic flux, and here has an n in front of it, but n is just equal to 1 since there's only one loop, then this works out to be mu naught I times the velocity, since the only thing here, this time dependence, is that x portion here, so that I have a x dt, which is velocity, divided by 2 pi times the natural log of the length factors. So plug in our numbers, which is what we didn't do last time, and it turns out to be 2.4 times 10 to the minus 4 volts. So good. So the next part then says, what is the induced current? Well, we know the induced current is simply equal to the induced EMF divided by the resistance. So if I plug that in, this becomes mu naught I times the velocity divided by 2 pi times the resistance times then the natural log of the length plus A divided by A. Plug in my numbers. Get in this case then is, once I open this thing up. So this works out to be about 6 microamps. And remember, micro is 10 to the minus 6. So it's the same thing as, put it over here. So 6 times 10 to the minus 6 amps. Not too bad. So this is the induced current inside of the loop. So let's talk about the direction of that induced current. So what's happening here is my magnetic field points outward, but here, since I'm moving this guy to the left, that means the area is getting bigger under this motional EMF, which means the flux is getting bigger. So since the flux is getting bigger, Lenz's law says we have to induce a magnetic field into the board in that case to counteract that increasing magnetic flux, which means the direction of our induced magnetic field then will be in the direction then opposite to the exterior magnetic field. And then right here, rule number 3 says that if I want to define the direction of the current, I put my thumb in the direction of the induced magnetic field. My fingers would then curl around in the direction of the current, which means in this case, my current is flowing in the clockwise direction. So inside of the rod itself, it's going in this direction. So this is the induced currents. So part C then wants to know, well, how much energy am I losing? Because this thing has current running through it. So I have to have power that is then radiated because I have current which is flowing through a resistor. And we know that's equal to simply the EMF squared divided by the resistance. So if I plug in all my stuff, that's this thing squared. So it's going to be a mu naught squared, current squared, velocity squared divided by 4 pi squared. And then I get a resistance, so that's simply resistance times the natural log of L plus A divided by A, and that quantity squared. So all that stuff squared simply divided by the resistance. Plug in my numbers. What again in this case then is the power loss is about 1.44 times 10 to the minus 7 watts, which is roughly about, what? Over 1. So it's about 0.014 microwatts. So that's how much energy how much power, or the rate at which energy is being lost due to the resistance in the rod. So that's part C. Not too bad. Part D then says, okay, so what's going to happen is as this thing moves, so let's go back to our picture, I now have current which is running upwards through the rod. It's in an external magnetic field, so I have a rod which is carrying current in an external magnetic field, which means it has to feel a force. The direction of the force then is going to be given by our right-hand rule. So in this case, we put our fingers in the direction of the current, curl towards the external magnetic field. In this case, the external magnetic field is coming out. So I got to rotate my body, curl towards the external magnetic field, which means my force in this case is pulling it back in this direction. So here, my magnetic force then, which develops inside of the rod, is going to be counter the direction at which I want it to move. So the question then goes on to say, well then what external force must I then pull onto the rod to ensure that it moves with this 5 meters per second velocity? So that means that we have to pull on it in the opposite direction, in this direction, with an external force. Now, since I want the velocity to be equal to constant, what that means is that this acceleration must be equal to 0, which means that the external force then must be equal to the to the magnetic force, which means that, going back to here, what this means then is that the magnitude of my external force must be equal to the magnitude of my magnetic force, since the velocity is equal to a constant. So since v is equal to a constant, a then must be equal to 0. No acceleration. Now, what I wrote up here are some question marks, which is saying that, can I simply say that the magnetic force in this case is the induced current times the length crossed by the external magnetic field? So what was the caveat to use that force? Well, the caveat here was that our wire had to be straight. Even if I can't draw straight, the rod is straight, okay? So that satisfies that caveat. But the other caveat was that the magnetic field here had to be constant. In this case, this magnetic field is surely not constant. Right? Because again, the magnetic field up here is much stronger than the magnetic field down here, which means we can't actually use that version of the magnetic force. We're gonna have to instead integrate, which means we're gonna have to say that this is equal to the integral of the induced current times the length crossed then by the external magnetic field. And this is actually the differential length. Now, in this case, we already know the direction, which means that we only want to know the magnitude of this. I'm going to go ahead and put some absolute value bars across here, which means that this is then equal to the integral of the induced current times the differential length times the external magnetic field times sine of the angle between the two. So I get a sine from my cross product. Now, in this case, what's happening is what? My magnetic field is pointing that way. My current is pointing that way. So what's the angle between the two? 90. So sine of 90 is simply equal to 1. So this term here is simply 1. Now let's go back to our integral. The other thing we know about the induced current is the induced current has nothing to do with being position or time dependent. It's simply equal to a constant, which means that we can actually factor it outside of the integral. So this is actually equal to the induced current, which is a constant, times the integral then of dl integrated over d. Now in this case, what's dl? So dl, remember, is in the direction of the current, which means dl is a small slice across here, which is pointing actually in the radial direction. So here my dl is going to be this small little section here. So dl then is going to be equal to dr. So this is simply going to be dr, which is the length, differential length in the vertical, or at least this part in the radial direction, if I can actually speak. So good, so we know that guy. So here we're going to have dl is simply equal to dr. And we know this is a magnetic field from a wire, which means magnetic field from the wire is mu naught I divided by 2 pi. So let's put those two things together. So what this says then is our force then is going to be equal to the induced current times mu naught divided by 2 pi, those are all constants, integral from a to L plus a of then dr divided by n. Now, this guy we know is simply equal to what? Natural log. So it's going to be the natural log of L plus A. Let me erase this guy for now. So this means then that's what? My external force is equal to the induced current times mu naught divided by 2 pi times then the natural log of L plus A divided by A. Okay. So finally, if I go back to what I induced was, let me quickly go back a couple pages here. So again, I induced is equal to mu naught I V divided by 2 pi R times the natural log of that stuff. So let's plug all that in. So this finally becomes mu naught squared times I times V divided by 4 times pi squared times the natural log of L plus A divided by A quantity squared. Make sure the whole thing is squared. Plug in our numbers. Find in this case is that the external force then has to be equal to about 2.87 times 10 to the minus 8 newtons. So this is my external force. Okay. I feel like I forgot an I here. Units. No, that's I induced. Okay. No, that's fine. That was okay. Finally, part D, I think it is, asks for, no, sorry, part E is asking for the rate at which power is being added. So here we want to know what is the rate at which this external force is adding energy to the system. Again, we know this is simply going to be equal to the external force dotted by the velocity. But in this case, we go back to our picture. We know that the velocity is in the same direction as the external force. These guys are simply parallel, which means that cosine is going to be equal to 1. So this is going to be equal to external force times the velocity. So if I plug all that in, this works out to be about 1.44 times 10 to the minus 8 watts. And this is my power. What's up?
I have a question. How do you turn like the way that I induced is going when you said it was going clockwise?
Oh, how do we induce that? Okay, so remember, Lenz's law says that the direction of the induced magnetic field will always be opposite to the direction of the change of the external force. So what's happening here is since this rod is moving in this direction, this effective area then is getting bigger from moment to moment to moment. Since that area is getting bigger, what that means then is that the flux is getting bigger. So since the flux is getting bigger, that's effectively like saying that this thing is getting bigger over time. So since the magnetic field is getting bigger over time, I have to induce a magnetic field in the opposite direction to counteract that increasing magnetic field. So in that case, my magnetic field then has to point inward. Once I establish the direction in which it's pointing inward, then I put my thumb in the direction of that induced magnetic field, and my fingers then curl around in the direction of the current. So there's multiple things that you have to kind of pay attention to. So we have to pay attention to the direction this guy's pointing. What's happening here, is it increasing or decreasing? Once we know that, then we can determine the direction of him based off the fact as is he's increasing or decreasing. So there's a lot of little kind of intricate things that we have to kind of pay attention to. Molly. It's constant, correct. So what I mean in that case, as far as spatially concerned. So what's happening here is since it's moving at a constant velocity, that's constant. The current inside of the wire is constant. Mu naught's constant, 2 pi is constant. R is the resistance of the rod, which is also constant, which I'm at least pretending it's constant. But as it gets hotter, the resistance is actually going to change. So that's actually temperature and time dependent, but we're going to ignore that. L is a constant. That's just the length overall between the two different conducting rails. And A is just that distance. So everything there, as far as the current is concerned, is constant. Now, the only way the current wouldn't be constant is if the velocity was non-constant. So if I was pulling it, for example, instead of pulling it at a constant velocity of v, let's say it started off here and I simply pushed it. Well, if I pushed it, what will happen here is that this magnetic force is going to start to counteract it, which means it's going to have an acceleration pointing in the direction of the magnetic force, which means this thing is actually going to slow down and stop. So that's the necessity of the external force to make sure that this thing moves at constant speed. Or I could always pull the external force, which is greater than the magnetic force, causing it to actually accelerate in that case as well. So here I'm only applying an external force to keep it moving at a constant rate. Does that make sense? Now, as far as the integral is concerned, again, nothing here is actually position dependent. We already did that integral over the position, which means everything here has no r, little r variable to it. So in this case, the current is actually both position and time independent. It doesn't depend on either one of those. That won't always be the case. But don't worry, as far as the exam is concerned, I won't give it anything that's hard. It'll be great. Even though I think I told you guys before, this was an exam question a long time ago. But I haven't been that mean in a long time. What's up, Greg?
If the induced like flips to counterclockwise, does that make it negative current, or is it just?
Well, what happened in that case, if it was going to switch the directions, what that basically means is that the only way to get it to do that is if this area was getting smaller. So in that case, if I was actually pushing it in this direction, the area would be getting smaller. So in that case, the flux would be getting smaller. So my D induced would have to be in the same direction as the external, which means in that case, I'd have to go this way, which means my current would go around in the counterclockwise direction. So the induced current will always be induced in such a way to counteract the change. Never in the same way as the change. That's what happens with the electric field, but we'll talk about that after the next exam. Okay. We clear up some of those questions. All right. So Faraday's law, not very easy, but it's manageable. So it's not too bad. So next thing is, let's do some group assignments. Let you guys see how you're actually doing with all this stuff. Oops, wrong one. So I have 3 of them for you. Here's the first 2, and I already drew pictures, so I'll explain. This velocity is not right. I had it right on the yellow sheet. So this says that we have a conducting rod of mass 0.75 kilograms and resistance 1 ohm is pulled horizontally across 2 frictionless parallel rails, which are separated by a distance of 12 centimeters, by a massless string, which passes over a massless pulley and is connected to a block of 7 kilograms in a uniform external magnetic field that's vertically oriented with a magnitude of 1 Tesla. So it says the bar then is released from rest. What is the terminal speed that this thing is going to reach? So let's look at the beautiful picture I drew first. So here are my conducting rails. That's these guys. Here's the mass, which is then being pulled horizontally across it. Now, again, this is a massless string, which then goes over a massless pulley, which then is connected to the 7 kilograms. And then the magnetic field is pointing upward, which is then 1 Tesla worth of magnitude. Or here's a top look at it. Here's my 2 conducting rails. These guys are separated by a length of 12 centimeters. Here's my string. This guy's going to be pulled in this direction. So what's going to happen? What's going to happen is, initially when this thing is at rest, there is no magnetic force counteracting the direction at which this thing is going to move, which means this thing is going to start to accelerate. And it's going to start to accelerate because of this mass here. This mass is going to keep pulling down, but as it starts to move further and further and further, current is going to be induced inside of this wire because this forms a closed loop, which means the flux is going to be getting bigger, which means the induced magnetic field has to be into the board, which means this thing is going to feel a drag force due to the magnetic force. The faster this thing starts to move, because of this acceleration here, the bigger this magnetic force is going to become, which means the velocity is going to get bigger and bigger and bigger and bigger until eventually what's going to happen is you hit what's called terminal velocity. And remember what terminal velocity means, what we talked about last semester, is when the acceleration goes to 0. So what's going to happen is this thing is going to continue to accelerate with a time-dependent acceleration until eventually the acceleration is going to go to 0, at which point in time, the magnetic force will then equal the gravitational force. So when this thing hits terminal velocity, what will happen then is that the magnetic force pulling back in this direction is going to match the tension at which this thing is being pulled at. And the tension in this case is simply equal to the weight of this block. So when the acceleration goes to 0, the tension here is the same as the weight here, which is the same as the tension here, which has to be the same as the magnetic force. So basically all you're doing in this case then is what? Setting the magnetic force equal to the weight, and then solve for the terminal velocity. So that's when it occurs at terminal velocity. So what you should find, I redid this morning, your terminal velocity should be about 4,763.9 meters per second. That's how fast this thing is going to reach. Go, let's talk about the second one. So the second one says we have an 8x8 square loop is halfway into a magnetic field perpendicular to the plane of the loop. The loop's mass is 10 grams and has a resistance of 0.01 ohms. A switch is closed at time is equal to 0 seconds, causing a magnetic field to go from 0 up to 1 Tesla in 0.1 or 0.01 seconds. So from here, what I want to know is what is the induced current in the loop due to this time-changing magnetic flux, and then with what speed is the loop kicked out away from the magnetic field? So let me talk about that picture. Let's draw that one. So here's my 8x8 loop. Half of it is in an external magnetic field, which I chose to be pointing out. The other half has 0 magnetic field. So again, what's going to happen is at time is equal to 0, I have 0 magnetic field. I'm going to close the switch. That switch then is going to crank up the magnetic field from 0 up to its maximum of 1 Tesla in a time frame of 0.01 seconds. What that's going to do is it's going to cause a current to move through this loop. That current then is going to cause a force onto this guy. It turns out the magnetic force is going to point in this direction, causing this guy to then jump out of the magnetic field. So what you want to find then is what is the velocity at which this thing jumps out of the magnetic field region. Anybody ever heard of a railgun before? This is a railgun. It's basically a prototype of a railgun. Railgun is you take a metal disc, you basically put that onto a cylinder, and then you crank up the magnetic field from 0 up to some unknown quantity, which then causes the ring to accelerate away. And then you use those rings as basically projectiles. Hence a railgun. This is basically a railgun. So this is the third one. So here you want to know what is the current, which is induced. Here, assume that this thing changes at a constant rate, which means the change in magnetic field divided by the change in time is constant. Hence the change in magnetic flux is constant. Good. So that's the third one, or sorry, the second one. The third one says, let's bring up the third one. So this says, what is the induced EMF generated by a rigid rod of length L, which is rotating perpendicular to an external magnetic field with constant angular velocity omega? So let's draw that picture. So this picture says, here's my rod. My rod has a length of L. This is the pivot point. This thing is simply going to rotate around in a circle with constant angular velocity of omega in the external magnetic field, which again, I chose to go out of the board. So in this case, I want you to find what is the induced EMF throughout the rod. The answer is 1/2 B times omega times L squared. I'll tell you how to actually do this one. I'll get you guys started. So note that the total EMF is going to be equal to the integral over all differential EMFs. Which basically means that what you're going to do is you're going to chop this thing up to a small section. So here's my subsection, where this has a length of DL to it. And then what you're going to say is at this moment of time, this thing is moving in this direction with an instantaneous velocity of V. So what this means then is that the differential or the small amount of EMF contained inside of here is then going to be equal to, this is now just a straight rod moving in an external magnetic field. So this is going to be equal to the magnetic field times the velocity times the differential length. But if this distance from here to here is the distance L, then we know that V is related to omega by the length L, which means the differential amount of flux, which is generated, or sorry, EMF, which is generated in that piece, is then going to be B times omega times L times dl. Now, all you're going to do is take this guy, shove it in here, integrate from 0 to L, and you're done. That's about it. So, I'll give you time to work on it. So either I'll give you the whole time or I'll cut you off at some point. We'll see how things are going. Because there's about 25 minutes left, I think, with 3 of these things to work on. So I might cut you off a little bit with like 5 minutes left to kind of talk about a little bit about eddy currents, but we'll see what happens. If not, we'll do those next time on Wednesday. Let me bring up the first one. That guy first. Any actual questions are on Blackboard. We need to break those up. Yeah, so this is just basically a straight wire and a constant external magnetic field. So that means that your F is then going to be I times L times B. Because I is perpendicular to B. So that's sine of theta particle. But in this case, I is going to be the I induced. And then I induced is going to be the induced EMF divided by the resistance. But we already looked at events before as well, so we know that the induced EMF is that of a straight rod moving in an external magnetic field. So it's just the magnetic field times the length times the velocity. And now set all that equal in. Right. In this case, since it's moving, so the rod moving in an external constant magnetic field, it's just the yes, means the velocity which you're looking for. L is just the 12 centimeters. Yeah, so I'm induced would just be that divided by the resistance. Well, you're going to eventually take that with the force instead of equal. Yeah. So you already did that there. You did. Yes, that's right. And then use the magnetic force as well. The magnetic force is idle plus B. Yeah, so in this case, I is I induced. Sure. So I think I have the right answer. Pretty close. So how does it with this? Well, that doesn't mean you're right. Oh, sorry. You were just on there right. So that should be B. And then divided by reason. Resistance was 1. Yes. So it doesn't change your number, but it changes. Yeah. No. Okay. Just really lost right now. All right. So let's talk about this in stages, shall we? So let's look at the top view. Again, B is in this direction. The rod is moving to the right, which means the flux is getting bigger. So we know that B induced has to be into the page. So if it's into the page, that means the current is going in this direction. So I have current going in this direction through here. So this is I induced, right? Which means here I induced is coming out towards us. Now, since I induced is coming out towards us, we put our fingers in the direction of I, curl towards B, which means our thumb is giving the direction of the magnetic force. So in this case, this thing has a magnetic force in this direction, right? Okay? Cool. Now, what we said was that terminal velocity says the acceleration has to be equal to 0. So let's look at it at terminal velocity. So at V terminal. So for V terminal, what's going to happen is this thing's going to have a tension pulling in this direction. Right? So the acceleration is equal to 0. So what that says then is by Newton's second law, the sum of the forces in the x direction is equal to 0. If this is my x direction. So I get my tension minus my magnetic force is equal to 0, which means the tension then is equal to the magnetic force. Okay? Tension, in this case, is going to come from this diagram. So from this diagram, this is capital M. So I got mg down in this direction, tension up in this direction. Since the acceleration is equal to 0, it means my tension then is equal to simply mg. Okay? Magnetic force, we know, is equal to the induced currents times the length crossed by the external magnetic field. But in this case, since magnetic field is this way, current is this way, the angle between the two of those is simply 90 degrees. So this is going to be equal to the induced currents times the length times the magnetic field. Okay? So, bracket here. So this means that mg then is equal to I induced times the length times the magnetic field. Okay? So good. Good. Now, what is I induced? Well, I induced we know by Ampere's law is equal to the EMF divided by the resistance. The EMF we know is a straight rod moving in an external magnetic field, which means that's simply equal to BL. So this says this is going to be equal to B squared L squared times the terminal velocity divided by the resistance. Solve that for terminal velocity. It's just a 205 problem. Just 205. Yes.
You didn't say B, you said B.
I said V?
Yeah.
Oh, I said B, you just might have heard
B.
Gotcha.
Like, I'm so confused. So, B.
I'll bring my son and we can work on our phonics. That was okay? So I'll bring up the second one. I'll give you a hint on this one. That's the direction of beat.
For which one?
No, he was playing in one Tesla. No, so this is just a constant next time. Just one Tesla. Sure. Yeah, I smudged it when I was doing something. So that's 0.00 or 0.01. That's actually 0. Let me look at the question. Maybe 0, 0. I don't know. That's fine. Yeah, 1, 0. 0.01. Okay, and what's the second question? There you go. So if you haven't picked up on it yet, this exam is kind of humorous for me to watch you guys take it because of all the right-hand rules. So I get to watch you do this in the middle of class. It's great. So it's about the most excitement I get the entire semester. So. Just remember, all you righties on the exam, it's called the right-hand rule, not the left-hand rule. So this is one of those exams where if you're left-handed, you actually have an advantage because you don't have to put down your pencil. Well, good.
I guess the first thing really trips me. I don't have time figuring out what equations.
Okay, so here, let's start off with the fundamentals. So determine what is the induced EMF. So you know the induced EMF is the time rate of change of the magnetic flux times the number of loops. Here, there's only one loop, so the number of loops. So the first place let's start off would be determine what is the time rate of change of the magnetic flux. That'd be the first place. Or what is the magnetic flux? So here the magnetic flux is, well, initially, half of the square is in there. So that means that the initial magnetic flux is what? Magnetic field times half of L squared. That's my initial magnetic flux. What's the final amount of magnetic flux? Well, 0. Once it jumps out of the magnetic field region, it's going to go to 0. So that means my change in magnetic flux is I'm going to be 0 minus the initial, which is 1/2 B times L squared. So that's my change in magnetic flux. Okay. Now my rate of change of magnetic flux is then that divided by the change in time, which is 0.01. So then my induced EMF is equal to negative of that. So it just basically gets rid of that negative sign. Once I know the EMF, then I know the current by Ohm's law is simply that EMF divided by the resistance. So always a good place to kind of start is when you're dealing with problems like this. What's the EMF? Where am I going to get that from? So that comes from the flux, more appropriately the rate of change. So this one you don't ever need, but you keep it short. So L is 0.12 G. Yes, for ions. Yep. Okay. And you know what R is? That's 0.01. L is 0.08, because that's 8 centimeters. And B is what? 1 Tesla. Okay. We'll have a little helper there. In this case, the initial is 0.
for IND.
Yep. 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 Oh, so we're assuming the rate of change of the EMF is, or of the flux is constant, which means that EMF is also minus change in magnetic flux that I change. So like equals. So your initial, so the change in magnetic flux then is equal to the final magnetic flux minus the initial magnetic flux. What we're assuming is that it jumps out of the magnetic field region, which means the final magnetic flux is zero. The initial is how much? That's right. Okay. Well, you don't care about the time. So, well, yeah, it's going to jump up to, so we're going to assume that the magnetic field is the 1 Tesla. So it starts at 1 Tesla. So we know that the magnetic field is going to be 1 Tesla. Okay, that's fine. Gotcha. Times the area, but the area is half of that area. Well, then there's no point. Sounds like this end of that. So we're going to assume that the goes up to the maximum. Okay. So the velocity, that's when you have to say, okay, the magnetic force is pushing 2 electrons, which means we know by Newton's second law, the magnetic force has to be equal to Newton's second law. So in this case, I already wrote out what A was. So A is going to be equal to the average velocity divided by the change in time. Where the average velocity is going to be the same thing as the final velocity, which is what we're looking for, plus the initial velocity, which is 0 divided by 2. Okay. So basically, now all we got to do is put all those pieces together. So everything is almost done. So finally, what I have is magnetic force is equal to mv over 2 delta t. Magnetic force, this is a straight wire in an external magnetic field. So the same force you used in the previous problem. So finally, we're going to have induced times L and B is equal to mv over 2 delta t. Solve for It's just a straight wire which is carrying current. Yeah. So the top and bottom portions are going to cancel each other. So the only portion of the magnetic force which will be not canceled will be the one on that 8 centimeters worth of. That's it.
That side.
You mean for the magnetic force?
Like if you're trying to find area.
Oh, if you're trying to find area, yeah. Then
it's just a.
Well, it just takes half of the area of the square.
Yeah. That's easier to do it now.
So instead of L squared, it's L squared. Is doing all right? So don't worry, Wednesday, this stuff's going to get even more exciting. We'll finally talk about the relationship between the electric field and the magnetic field. More exciting. It's okay. All right. right, so we're not going to talk about eddy currents today, so we'll do that first thing on Wednesday morning. So I'll show you a couple videos, and we'll talk about eddy currents. Eddy currents are pretty cool stuff, so we'll look at those. And then after that, we'll talk about the relationship then between the electric field and the magnetic field. So what you're actually inducing is an electric field. We'll talk about how that actually works. And then we'll start talking about inductors. So it will be great. Okay. So have a good day, everyone. I will see everyone on Wednesday. It'll be great.